Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. In the context of CC cross coupling reactions, we have been discussing various types of cross coupling reactions. These are mainly the palladium mediated cross coupling reactions starting from Heck, Suzuki, and today we are going to take up another interesting reactions, which is the Stille cross coupling reaction. Let me reiterate, at the heart of this palladium mediated cross coupling reaction resides the fact that these are highly selective reactions, in the sense that they give cross coupled products, and that these reactions have a broad applicability in terms of the reagents being tolerant towards various functional groups, as well as this chemistry is much more or less out of the glove box, dry box chemistry. So, can be performed under aerobic conditions in open laboratories, as well as palladium does not having any toxicity issues associated with it. These palladium mediated cross coupling reactions have are in turn a hit in terms of the popularity and the usage of this chemistry. We had in that context we have analyzed Heck coupling reaction as well as Suzuki reaction in our last two lecture, and today we are going to take up another such important cross coupling reaction, which is the Stille reaction. In the Stille coupling, 10 organyls are used, and these are mixed substituted 10 organyls which are used for Stille coupling. So, there would be, these are organyl compounds of 10, but they may have more than one kind of ligand. So, uses mixed substituent tin organelles. Example R, SN, Me3. So, there are two different kinds of organic moiety attached to tin, and these Stille coupling also is functional group tolerant, and uses mild reaction conditions, and are used in synthesis of biaryl compounds and also various macrocycles and so forth. So, actually Stille coupling is also one of the preferred method for performing this palladium mediated cross coupling reaction, and the Stille coupling in general is given by this following equation: R1x plus R2 SN R3 give in presence of palladium 0 Ln giving R1 R2 plus R3 3 SN X, where X is an halide like bromine, iodide, or triflet O SO2 CF3. Now, one thing which is characteristic of to note in Stille coupling is that this organotin reagent, though is a mixed substituted, that means it has two different kind of organic moiety attached to the tin, only one gets transferred in the cross coupling reaction. For example, in this case R2 gets coupled, whereas R3 stays on the tin. So, it is just transfer of one of the organic moiety from this mixed tin organyl compound that really happen in the cross coupling reaction. Now, one thing which is common for most of the cross coupling reaction is, as I mentioned earlier, is its mechanism, that the mechanistic pathway more or less remains the same in material of different kinds of cross coupling reaction, and that why all of these cross coupling reaction are sort of clubbed under one platform. Now, that being the case, the logic used to solve a particular challenge in one cross coupling reaction is equally effective in solving the similar challenge in another cross coupling reaction. A nice demonstration of that we had seen Buchwald's ligand in the last discussion on Suzuki, where Buchwald had used a electron rich bulky phosphine ligand, where in which case the electron richness of the ligand was used to facilitate the first step of the oxidative addition reaction, whereas the bulky nature of the ligand was used to facilitate the last step, the reductive elimination step of the Suzuki catalysis cycle. And as a result, when both of these work in synergy, the catalyst so developed by Buchwald could easily carry out a very challenging Suzuki reaction of aryl chlorides. Now, given the fact that the catalytic mechanism for Suzuki and Stille, the one that we are discussing right now, are quite similar, in that case obviously the similar choice of bulky ligand with basic additive can also make the Stille coupling of chlorides possible. So, that is exactly what is seen over here, that application of bulky phosphine like TBU whole 3P and basic additive cesium fluoride made the cross coupling of aryl chloride. Aryl chlorides possible. So, this was reported by Professor Gregory Fu, and this is exactly the same logic which was used for performing the room temperature Suzuki coupling of aryl chlorides. Exactly the same logic of using bulky phosphine with electron rich bulky phosphine can also be used in performing the Stille coupling of aryl chloride the similar way. Now, one important thing is for this Stille coupling, that the electrophile should not contain beta elimination pathway. So, these are some of the standard basic requirements of Stille coupling that would provide a favorable cross coupling reaction. The primary thing is that the electrophile or Rx should not contain beta hydride elimination pathway. And These Stille coupling is obviously functional group tolerant. And for example, groups like NO2, CN, OCH3, COR, CO2R, CO2H, CHO, etc. For functional group tolerance. Now, in terms of the nucleophile, which is organotin reagents, the following is the reactivity order. Of tin organelles. Now, the order is given as alkyl less than acetonyl less than benzyl, which is equal to allyl less than aryl less than alkenyl less than alkenyl. So, these are the reactivity order for the tin organyl. Now, this trend sort of resembles to the more carbanionic nature of the organyl which is bound to the tin. For example, alkyl is a sp3 a carbon attached to the tin, but in alkenyl it is sp carbon attached to the tin, alkenyl sp2, aryl sp2. So, what it turns out is the most S character is on the carbon attached to the tin, the more negative charge it will look more carbanic or more negative charge it will accrue, and as a result it sort of behaves as a better nucleophile in the cross coupling reaction with its electrophilic partner Rx. So, the idea is the reactivity of the tin organelles, the organelles which are more negative in terms of electron richness or electron density, they make better nucleophile as opposed to the alkyl ones or the acyl ones, which are not as that electron rich. So, this sort of is quite intuitive in the sense that this indeed in fact is a cross coupling reaction. So, the more nucleophile, more nucleophilic the organic moiety is, the better it would be to couple with the electrophilic count partner, which comes from the Rx. Okay. So, now we just had discussed about these the coupling requirement for the chlorosubstrates, the challenging aryl chloride coupling. The requirements for the challenging aryl chloride coupling is that for the challenging couplings is that the ligand should be electron rich and bulky. Ligand should be bulky and electron rich. Write TBU whole 3p, and then the presence of additive like basic additives is required. Like cesium fluoride is required for performing the chlorocoupling, the challenging chlorocoupling at room temperature, chlorocoupling under convenient conditions. So, apart from making this CC cross coupling bi-aryl, there are other scopes of Stille coupling available. For example, in presence of carbon monoxide, ketones are formed. So, we are going to see some of the scope as well as the reactivity of Stille coupling. So, in presence of CO, ketones are formed. So, this is beautifully illustrated by this example, in which R 1 X plus R 2 S N R 3 whole thrice, palladium 0 L N carbon monoxide giving R 1 CO R 2 plus R 3 S N X. Now, so this says that in presence of CO there is a formation of ketone. So, what one can see that the scope of Stille coupling also is quite large, that it cannot not only make the bi-aryl or CC coupling, but it also can results in formation of carbonyl compound ketones in presence of a reaction being done in presence of carbon monoxide. Now, let us sort of take a look at the mechanism that by which the Stille coupling proceeds, as that will provide an insight into the mode of the catalyst action, as well as it will enlighten us about the similarities and dissimilarities of Stille coupling with regard to the other cross coupling reactions, particularly the Suzuki one that we had discussed in our previous class. The reaction over here too, the catalyst precursor is a palladium 0 species, which is given by PdL2 . The first is obviously the oxidative addition of R 1 X. So, this is the oxidative addition step. To give this compound X PD L L R 1. The next step is the conversion of this cis compound to the trans compound, similar to what we had seen, that cis trans rearrangement. So, hereby it becomes a trans compound R 1 X. Now, the next step is the transmetallation step. This is the cis trans rearrangement step. And the next step is the transmetallation step that occur from R 2 SN PU 3, and this goes via concerted pathway through a transition state, which is shown over here. L R 2 SN BU via this transition state to give the compound Bu3 SNX along with the generation of PD L2 PD R1, and this compound in presence of L gives the reductive eliminated product R1 plus R1 plus R2. This is the cross coupled product. So, this step is the reductive elimination step. And the rate determining step, of course, is this attack of this R2 on this PD R1X. So, this is the RD step of the reaction, and this step proceeds by a concerted mechanism pathway as it seen over here, and this step is also popularly called as transmetallation reaction. So, this in a brief gives a glimpse of how the Stille coupling happens. First is the oxidative addition, then followed by the rearrangement from a cis to a trans, and then subsequently the attack of the rate determining step, in which R2 knocks out this X and produces palladium R1 R2 L, and generates in turn generates Bu3 SNX and L. Now, this R1 R2 already are in cis disposition. So, it really undergoes reductive elimination to give the desired product, which is R1 R2 coupled product. It is marked in red along with the formation of the starting precursor, which is PDL2. Now, this is sort of similar to what one sees in Suzuki as well, because there too there are 4 steps. One is oxidative addition, transmetallation, reductive rearrangement, and then reductive elimination. In this case, it is oxidative addition, rearrangement, reductive transmetallation, and reductive elimination. So, basically these 4 steps are quite similar to the steps, elementary steps, that what has been observed for the Suzuki coupling. Now, proceeding further, let us take a look at some of the examples, application oriented examples of Stille coupling. For example, it can be used for synthesizing ketones in presence of acyl chlorides. So, applications of Stille coupling: synthesis of ketones, so with acyl chloride ketones are obtained from acyl chlorides and tin organelles, and this can be used for sterically demanding as well as alpha beta unsaturated ketones. So, it is versatile, can be used for sterically demanding or alpha beta unsaturated ketones, and the best thing is that the final product it does not react with the organotin reagent. So, quite interestingly, the R2 SN Me3 does not react with ketone formed, and this is given by this equation which is R1 CO Cl plus Me3 SN R2 in PDLN giving R1 CO R2 plus Me3 SN Cl. Now, with this I would like to conclude today's discussion on Stille coupling. Today what we have looked upon is the touched upon is the reason for Stille coupling to be as effective as the Suzuki, in that sense that it uses mild conditions, and it instead of organoboron reagents which are used for Suzuki coupling, organotil reagents are used for Stille coupling. Furthermore, in Stille coupling, these organotin reagents are mixed substituted organelles, organotin substituents, and of these only one of the substituents gets transferred over to the transition metal and the other doesn't. Now, we have also looked into the order of the reactivity of the in terms of the electrophile, in terms of the electrophile, as well as we have looked at the reactivity of the organotin reagent, and what we have seen that sp carbon is more nucleophilic or better performing than sp2 carbon moieties, which is obviously better performing than sp3 ones, and this is in line with the greater s character on the carbon, making it more electron rich as opposed to and that decreases on going from sp to sp2 to sp3. We have also seen that in presence of carbon monoxide, the scope of the reaction can be extended from just simply producing biaryls or bialkyls or alkyl aldyls. One can also get ketones if the reaction is performed in presence of carbonyl CO gas, and same thing if the reaction is performed with acid chloride, again one can also get ketones. We have seen the example of it. We have also looked at the mechanism of Stille coupling, and what we had seen that this mechanism is somewhat similar to that of the Suzuki coupling in terms of the presence of the 4 elementary steps, which are oxidative addition, transmetallation, rearrangement, and then reductive elimination. And the logic, we have also noted that the logic which was used to achieve Suzuki coupling of aryl chlorides was also equally effectively used for achieving Stille coupling of aryl chlorides, and the logic being the use of electron rich and bulky phosphine based ligands, which the electron richness of the phosphine ligand would facilitate the oxidative addition step, whereas the steric bulk of the phosphine ligand would facilitate the last step, which is the reductive elimination step. So, with these I would like to conclude today's discussion on Stille coupling, and I am going to take up some more applications of Stille coupling to highlight its effectivity in in various CC coupling reaction in the next class. And then I will also touch upon another important CC coupling reaction, which is the Sonogashira coupling. So, with this once again I would like to thank you for being with me in this class, and I look forward to discuss more on the Stille coupling, and then take up another new coupling, which is Sonogashira coupling when we meet next time. Till then, goodbye and thank you.